next topic is called as the flat top sampling. Okay, here, compared to our yesterday's discussion, where the sampling of the signal, sampling of an analog signal using the natural sampling technique results in samples of certain width, say capital T, whose amplitude varies according to the changes in the amplitude of the original signal, right? So that was a natural sampling. Now we have a slight difference coming into picture, wherein the sampled value will be held for certain duration. There will be no change in the amplitude of the sampled pulse. So the top of our samples will be horizontal. Okay, that's why it is called as a flat top sample. Anyway, we'll come to that. We'll start from the ideal sampling once again. Okay, so this is what we already know, so we'll start from that. We know that the the ideal sampling, the ideal sampling is done by, so we multiply, so this is multiplying the original signal that is denoted by g of t, original analog signal, that is g of t, by impulse train. Impulse train, what are the characteristics of impulse train? The impulse train which separated by a specific period denoted by capital Ts. Impulse train, I can directly write, separated Ts, sampling duration, Ts seconds. So let us try to denote that mathematically. So this also equation we already have seen, right? So that is G delta of t is equal to G of t into the impulse train denoted by, this is n is equal to minus infinity to plus infinity. This is delta of t minus n into ts. So that means this is equal to the summation. You can see I can bring the g of t inside the summation, and I can replace the t by every position where the delta t exists. Correct? So that means I can rewrite that as nts. So how do I write? Summation remains same. N is equal to minus infinity to plus infinity. G of nts into delta of t minus n into ts. Okay, so let's hold on to this equation for some time. Let's try to recall what we had studied basically. So in this equation number one, so here the g of nts, it represents the weight of each impulses. So each impulse get multiplied by a g of nts, which acts like a weight for it. Correct? Weight means it's getting multiplied by a scaling factor, right? So we can call it as a weight. So g of nts represents the weight of impulses. Again, I can see that this weighting of the weight function gets multiplied to delta function wherever the delta function exists. That's all. Okay. So here the g of nts, this represents the weight. Okay, weight of impulses, right? Those impulses which are separated, which are separated by capital Ts. Right. Now, let us try to change the scenario here. Instead of using the impulse, right, let us try to use the small rectangular pulses, right, whose amplitude will be g of nts and width is equal to still t, right? But it's something like you are trying to replace impulses by the stretched rectangular pulses of certain length, say denote that as say capital T. Okay, now so let's try to write that first, then we'll see how I come to the flat top concept. All right. Okay. Right. So uh, we we replace the impulses, the rectangular pulses in practical situations. This is obvious, right? And these rectangular pulses will have an amplitude that is again getting multiplied by g of nts, and there will be a width equal to capital T seconds, right? So the the rectangular pulses are of amplitudes denoted by g of nts. Okay, that's the scaling factor once again coming into picture, right? Are of amplitude this, and what's the other point? You need a width, right? And they're of width which equal to capital T seconds, right? So so we saw the concept yesterday that we will be considering the impulses also as rectangular pulses only, but you see that becomes uh, non-realizable, right? Because of the width of the pulse being equal to zero. That's the only thing. Now we have a small stretched rectangular uh, uh, width for the pulse, right? So that they become hardware friendly and it is implementable. You can implement that. Okay. Now you see we consider that it's a rectangular pulse and it has an amplitude g of nts. That means it is fixed. Amplitude is not changing at the moment of sampling. Whatever value is there, it will be held. Okay, so that value will be held by the rectangular pulse for some duration. That duration is equal to t. I'm going to show you that. All right, let's draw this diagram later. Okay, so okay, let's solve the diagram now itself, right? So we have we need two different graphs. Okay, the graph number one, this is for the first graph, and let's assume that the first graph has, so this is the time axis, and I will also draw another axis for the second graph. Okay, so this is the t, right? The first one is the original signal denoted by g of t. Okay, so let me plot it in this way. This is the function. Okay, original function. Right. Now, okay, let me this is what I want, and again I will copy the same thing below because I'm trying to sample that out. All right. So just for the sake of sampling, I will copy this part. All right. Now what we do, we'll do this sampling, but you see this is going to be the flat top sampling. So from the top, I'll sample it with some pulse width. I'll show you the pulse width as well. Now you see the amplitude is not going to change. It's going to be a fixed one like this. So I'll show you that again. Maybe I'll do the sampling over here. So you can observe that at this point, this is the sampling point, whichever is the sampling point, the value will be held, right, for certain duration. It's not going to follow the waveform like this, right? Previously, we saw that this is going to follow this and, right, like something like this we had, right, earlier, right? So now you see that portion is not there here. It's going to hold only that sample, the value for certain duration. See the difference, right? So that's the difference between the natural sampling and this. Okay, again, so this is the sampled value. It will be held for certain duration. So this repeats all the way throughout the sampling process. All right, initial value will be held. In the middle, if it changes, right, that change will never be considered, like this. So here it's very clear that signal amplitude is lesser than the sampled uh, point at which you are sampling, but right, that's not going to be considered. That's all. Like this, we have the various samples taken. That moment, whatever value is there, it will be. So this is the way of representing this. Now I'll give a new notation. So we'll call this as the say S of t, the sampled result, right? And we have certain we know something about the pulses, right? The each of these pulse has a width that is equal to capital T, and let us try to assume in this way: the sample happens at 0. This is TS, 2 TS. That's, it's not the midpoint. You see, it's the starting point. Okay, so like this will be 3 TS. It's 4 TS, 5 times TS, and so on. Each pulse has a fixed width that is equal to capital T, and each pulse is repeated at ts seconds, like ts2, ts3, ts. Even on the negative side this will be there, right? Like minus ts, minus 2 ts, minus 3 ts, and so on. Okay, now okay, let's hold on to this. Let's continue our discussion, right? Let me write an equation for s of t. Already we have come across such equations. All right, let's try to write an equation, right? Let the s of t is let s of t is the sequence of flat top, sequence of the flat top samples, right? The samples generated because of this, right? And let's try to write an equation for that. That s of t should be equal to the, normally you multiply, you just make a change in our previous equation, that's all, right? So it's actually getting multiplied by the g of t with a series of rectangular pulses denoted by h of t minus nts. Okay, but anyway we know that the scaling factor is g of nts, so n is equal to minus infinity to plus infinity. The g of n into ts, it remains as it is, only the function, is changed now. It's not delta function, it's not delta of t minus nts, you denote it as h of t minus nts. So h of t is my rectangular pulse repeated every time, starting from minus infinity to plus infinity. For n, h of t minus nts. Put n is 0, h of t, which is the first pulse that I can see over here. So put n equal to 1, it's at ts, 2 ts, 3 ts, and so on. Right? So that's the representation. Even on the negative side, we expect, but as of now in this diagram, I have not shown both the signals present on the left side of the y-axis. But yes, definitely, as per the equation, n takes even the negative values. Okay, right? Now, so how did we come to this equation? I'll call this as equation number 2, right? We obtained this equation number 2 from equation number 1 itself, right? Simply replace the delta of t minus nts, that is the impulse functions in equation number 1 are replaced by the h of t, right? Where I'll write it. So here, where the h of t, right, represents the rectangular pulses of unit amplitude and duration equal to capital T, right? So where h of t, okay, let's try to write it in this way. H of t is the rectangular pulse of unit amplitude and the pulse width equal to capital T segments. Okay, now let's try to look at such a pulse so that we can try to write an equation for that. Okay, so that is, so as of now the pulse which we are looking at is like this. Okay, so this is h of t, amplitude being 1, right? And its width is 0 to t. So h of t versus t. Okay, so I can try to write an equation here, right? The h of t is equal to, I want to write two notations. One is a rectangular notation for that. Otherwise, I also want to write in terms of the values. So as of now, I can see here is something like this is one from where to where. So it's 1 0 less than or equal to t less than or equal to capital T, and I can say, right? So also this is 0 else. Okay, so this is 0 to t. This is my function, right? But if you remember the general function of rect t, this is how it's going to look like, right? So so okay, let me try to write here. But if I want to give a rect notation now, all right, so but the rect of t is like this. Okay, I'll write an equation here. So this is 1 for minus half less than or equal to t less than or equal to plus half, and this is going to be 0 else. This is the original format of a rect function. So just check that out. So this, sorry, I'll write it neatly. So the rect function, if you want to plot, this is the standard rect function which we are talking about. Now I want to give a rect notation for my h of t. But as of now, it's not possible because it's not in the standard format. What I'm writing now is the standard format of a rect function. So this is what I'm going to call as the rect of t. So the rect function will be, if you remember, it's something like this. It's present on both sides. Amplitude is 1, that's fine, and it is from between minus half to plus half. Now you can make a comparison, right? The comparison between the two functions, you can do this and this, you try to make a comparison. Now you can see that in the h of t, this is shifted to right and it is present between, say, 0 to capital T. That's the difference. So what's happening, right? You are scaling and shifting. Can you visualize the two operations here? One is a scaling because it's, so the width is how much? Width is actually 1 now. The width is, which is originally 1, becomes width equal to capital T. So that's the scaling, right? You are either compressing, or you are expanding, right? That is a scaling operation which we studied in the signals and systems. First thing. Second thing is that it's not just that, it is moved to right by certain units. Correct? So you can see that first we are scaling and then we are shifting, right? So you can shift it to right first so that it becomes 0 to 1, and then this becomes 1. When I shift it to right, it becomes 0 to 1 because minus half becomes 0 plus half becomes 1. Then you stretch it by a factor t, 1 becomes t, right? So that's what is basically happening over here. So therefore I can directly write an equation here which represents my function, right? Therefore h of t can be written as follows, right? This implies I can write h of t as you see, I'll directly use a rect notation. This is a rect function, but it's not t now, it is t divided by capital T. It's because of the scaling. And there is a right shift by how much unit? There is half unit. Okay, so rect of t by t minus half is our function. That's the h of t. Okay, absolutely fine. So we converted this into the rect function. Now we will do the analysis using this particular notation. This is the h of t in terms of equation, right? If you want to give an equation for the impulse, sorry, the sorry, yeah, the rectangular pulse which is being used in this concept, then the equation for that h of t should be this h of t, which is equal to rect of small t by capital T minus half. There is a division by capital T because I'm scaling by that amount, and minus half because I'm shifting to right by half unit, right, just to match my requirement. So that will be the conversion of rect of t to h of t, where h of t is written in the form of a rect function. All right, let's proceed further. Now you see, uh, this is happening. I will perform what is called as the convolution, right? So you see this equation, what we have here, it represents actually, right? It looks like a direct multiplication, but I'll come to that point. I'll look at that in the frequency domain by using the convolution first. Okay, all right. In the next step, we'll try to perform the convolution. Convolving, you see, if you use the impulse function for the sampling, right, I will be getting an answer that is g delta of t, right? This function I will multiply with, I will convolve with the h of t to get the actual results. That's what is happening here. So you see, I had the rectangle samples. After the sampling, maybe I obtained the rectangular samples of the signal. Sorry, original signal was this dotted line. I sampled ideally and I got this. Now in order to uh, get the flat top sample, this is extending something like this, means you are convolving the function with the results, right? You are convolving the rectangular function with the results. Okay, so that's how that's what is the representation. Anyway, you don't have to write this, but I'll give a notation for it for you here. So this is the g delta of t, let us assume. What I do, I try to perform the convolution of this function with our rectangle. Okay, this is the h of t. When you do this, right, what I get, I'll show you. So I'll copy this g delta of t once again, because that itself I can extend to show you the answer. Okay, so this is, I'll copy here. Right, now it is no more g delta of t. I'll just erase that part. And so wherever the function h of t exists, that will be replicated at the positions of the delta function. That means here I get one thing, here I get one more pulse, next pulse here, the third pulse here, fourth pulse here, and so on. You see that you got your flat top samples here. So ultimately, the g delta of t convolution with h of t is going to give me that answer. Okay, so this will be our s of t. Right. Anyway, you don't have to write this. This is that for your reference. But what I write here is convolving the g delta of t with h of t. So h of t is just defined. So we are trying to convolve that. Gives, I'll write here. So that is the g delta of t convolution h of t. So use the fundamental definition of convolution here. Let us not go with our equation which we were using so far. So far, whatever equation we use, let's forget that. We don't have equation 1 and 2 with us. Let's simply try to use the definition of the convolution to do the mathematics. And at the end, we will check that whether I get equation number 2 somehow or not. Okay. So that is, this is equal to, if you remember, this is integration minus infinity to plus infinity, because this is a convolution integral. Okay, integration minus infinity to infinity. The first function, that is g delta of You see, it's not t, it is a tau, right? You change your domain to some other variable, that is tau, into h of the second function is flipped, right, and shifted, correct? So h of t minus tau. So there is a shifting by an amount that is decided by t, and flipping gives you minus tau. So that is t minus tau t tau. Okay, let me call this as equation number 3 for our reference. Later on we'll come back. Now what we do here, we'll try to substitute, right, the one equation which we had earlier, right? So that is, we'll try to substitute the g delta of t into h of t minus 2, right? So g delta of t equation we'll write, but g delta of t is equal to, recall, right, we know this, we already have used this, that is n is equal to minus infinity to plus infinity. G delta of t is g of n ts into the delta of t minus n ts, correct? So this is equation number 4. So I'm going to put 4 in 3, right? So let's try to make that change. So when I put 4 in 3, this becomes, so I still have, okay, I'll slightly move down because there is less space here. I'll just move it here. Equation 4 in 3 gives me this equation. So on the left hand side, I still have the g delta of t convolution with h of t. On the right hand side, you see there is an integration which is already existing, minus infinity to plus infinity. Instead of g delta of tau, I am writing this, correct? So that means I have a summation from n is equal to minus infinity to plus infinity. This is g of n ts delta of, it's not t, it's tau now, so tau minus n into ts into h of t minus tau d tau. So by obvious means I need to solve this. So the best suitable approach that we have here is to make changes with the order of the integration and summation and see whether we can do something. Okay, so what I do, that is equal to, I'll bring the summation outside. Summation that is applicable for n is equal to minus infinity to plus infinity. The only term that has n is the g of n ts, so that I can bring it out, g of n ts. Okay, then the move the integration inside, that's for tau. So this is actually tau is equal to minus infinity to plus infinity. Every term that has tau should be inside this. So that is the delta of tau minus nts into h of t minus tau d tau. All right, now let me hold on to this. This is equation number, say, 5. We have what is called as a shifting property of the delta function, right? So that's what I am going to use now. There is a shifting property. It's something like, if you have integration from minus infinity to plus infinity, take a signal, say that is x of t, into delta of t minus t naught into dt. If you have something like this can be directly written as, you can see that there's a product, and the product exists only at t equal to t naught. So there is no meaning in doing the integration. This is simply x of t naught, right? I think we have used this a couple of times earlier. So this is the property that we are going to use. So I'll call this property by, say, equation number 6. So I'm using 6 in 5. Okay, so 6 in equation number 5 gives you, I still have the left hand side same, that is g delta of t, convolve that with the h of t, and on the RHS you can see that there is a summation which remains as it is, still the same. There is summation n equal to minus infinity to plus infinity g of n ts. This is fine for us. Now you see what happens. The right, the where is the h of t minus tau going to be present? It's going to be uh, present where the delta function exists. The value will be like that, correct? So I can try to write like this. You see here, this is the change I'm going to make in the above equation. It's the h of t minus tau itself, okay? But no need to do the integration. Simply put the variable tau is equal to n times ts. So that's what happened here. You see, the delta function existed at t naught, so replace t by that now, that value. So x of t. Now in this, in the above equation number 5, so integration is not happening with respect to t, it is with respect to tau, correct? So that means the delta function is at nts, so this nts should come to the tau position. That's all. So every tau has to be replaced as nts. That's where the delta function exists. That's all. That's what we did now. So let me know if you have any doubt. Otherwise, I'll proceed. Okay. So that means this is equal to, now I can directly write it as this is equal to n is equal to minus infinity to plus infinity. This is g of nts into h of, so see, this is t minus tau, every tau is replaced as nts, correct? So that is equation, let's call this as equation number 7. Okay, now so compare this, right? The RHS of this equation, equation number 7, that is summation n is minus infinity to plus infinity g of nts into h of t minus nts. That equation I'm going to compare with the equation number 2 we have written here. You see, it's the same. Equation 2 right hand side is also same, right? So that means the LHS of equation 2 should be equal to the LHS of equation number 7, correct? Both are same. So this uh, implies equation 2 is equal to equation number 7. So that gives, right, as a clear idea that the left hand sides are equal. S of t is equal to the g delta of t convolved with the h of t. So I already told you that this is how we obtain, right, by drawing the graphs here, but now I prove this. Okay, it's not simply saying that, okay, this is how you do, you get the answer. We prove that as well. Okay, so this equation means that the flat top samples can be obtained by convolving the output of ideal sampler with the rectangular pulse of unit amplitude and the duration equal to t seconds. That's what is the meaning. So let me call this is equation number 8. So this equation number 8 implies something to us. This implies the flat top samples could be obtained. That could be obtained by, we perform the convolution. So convolution of the output of an ideal sampler with which function? With a rectangular pulse. Okay, rectangular pulse of unit amplitude and duration equal to capital T seconds. Right. Now we need to visualize what's going to happen in the frequency domain. I want to know that whether in the Fourier representation of equation number 8, right, do I have the g of f, correct? The triangular pulse, right? So, sorry, the triangular spectrum should be present at the center, correct? It should not be located at any other points. I need a proper, what you call g of f, right, at the center, like we obtained in the previous section of natural sampling, right? There also, it's not a ideal sampling, it's a natural sampling. I obtained the triangular pulse, sorry, not the triangular pulse, that I obtained a triangular spectrum at the center of my frequency domain graph, right? If at all I'm going to get something like that, uh, even in this equation, right, whenever I try to perform the S of f, try to get the S of f, that means yes, I can reconstruct, because reconstruction is equally important as we have discussed so far, correct? So if I obtain the triangular pulse at the center, obviously that means yes, you can go back. So let's try to uh, get that. All right. So what we do now, we have to go to the frequency domain. So take a Fourier representation, right? So that is the Fourier transform of equation number 8. That should give you S of t is there. It should be S of f equals to, so G delta of t becomes capital G delta of f. Convolution becomes a multiplication h of t, h of f. Okay, straightforward. Let's call this as equation number 9. Now, so we already have an idea about the G delta of f, right, from our previous discussions, right? But the capital G delta of f is equal to, you see, fs into summation n is equal to minus infinity to plus infinity, capital G of f minus n times fs. So this is equation number 10. So try to put this back. So that means equation number 10 in equation number 9. That gives you S of f is equal to fs times the summation n is equal to minus infinity to plus infinity, the g of f minus n times fs into h of f. All right. Okay. I need a h of f now. I don't have h of f. First, I need to calculate that. Right. Let's hold on to this. Say equation number 11. Right. So now my idea is to find the h of f. Right. What you do, you try to take the Fourier representation of the h of t. Right. So to find h of f, we take the Fourier transform of h of t. So by applying the fundamental equation of the Fourier representation. That means h of f, any Fourier transform is nothing but it is integration all the way from minus infinity to plus infinity on the time axis. Take a function whose Fourier representation you want to take. In this case, that is h of t. Multiply that with a complex exponential function, that is e to the power minus j2 pi, is a complex periodic representation. It is continuous and it has a frequency f. So f is my frequency, t makes it as continuous function, integrate with respect to time. So this is t varying from minus infinity to plus infinity. Right, this is my basic equation. Let's try to do that. So you see, what we are, which is the function that we are looking at, right? So this is the function. This is the h of t versus t. So already we have written that, but just for my reference, I'm writing here. So this is my function. So amplitude is 1 and it is between 0 to t. This is the function whose frequency representation I want to find out. I want to see what are the frequencies present in this signal, right? So for which I am taking the Fourier transform. Okay, so that means now you see I can make a modification. This is not minus infinity to plus infinity. It is 0 to capital T. And between 0 to t, h of t has a value that is equal to 1. Okay, so that is 1 into, you will write e to the power minus j 2 pi f t dt. So becomes very simple integration for us, right? That means it is e to the power minus j 2 pi f into t divided by minus j 2 pi f, and I am substituting t is equal to 0 to t equal to capital T. That's the limit, correct? Okay, so let's try to simplify this. So this is going to be equal to, I'll write the 1 by j 2 pi f over there. So this is 1 minus 1 divided by j into 2 pi f. Put capital T over there. This becomes e to the power minus j 2 pi f capital T minus, put 0 over there, e to the power 0, which is 1. Okay, so we can simplify this further. There is okay, let us try to take the e to the power minus j pi ft outside. Okay, so that becomes okay, I'll multiply by minus 1 first, so that is 1 divided by j 2 pi f. This is 1 minus e to the power minus j 2 pi f capital T. Okay, so what I want I want to bring a sine or cosine wave format or something similar to that. For that reason, I'll try to take out e to the power uh, minus j pi f capital T outside. Okay, let me say the denominator is still the same, that is j 2 pi f. So here I'm going to get e to the power j pi ft minus one of the term has gone, has moved out, has been moved out. So you can see that it is minus j pi ft, right? Which function? You can replace this as e to the j theta minus e to the minus j theta, right? We have, so we use the following thing. If I have e to the j theta minus e to the minus j theta divided by 2j, yes, I can see a 2j here, right? So if I can utilize that, and this can be replaced by e to the j theta, e to the, okay, that's a sine function, so that is sine theta. So I'm using this, the above equation, to get this. So I have e to the power minus j pi ft into sine of pi f, sorry, capital T, pi f capital T divided by, if 2j goes out, it's simply pi f. Okay, you see I don't have a t here, so I multiply by t and I divide by t, so that I can bring a sinc function. Sinc of pi into something divided by the pi into something is sinc function, right? Sinc sine theta by theta, that's the format. So I can directly write, I'll try to write like this. The t which is there, I'll write it first, then I write a sinc function. The sinc function is nothing but remove the pi and write whatever is there, that is ft. Okay, sine pi theta by pi theta, if you have that, it's a sinc theta. Okay, so sinc of ft, and then you write e to the power minus j pi f capital T. So this is what is this? This is h of f, the frequency content of the h of t. So we had stopped at equation number 11, which had a h of f. You can see there. There we are going to substitute this now. So I'll call this as equation number 12, right? Okay, yeah, that's 11. This is 12. Fine. So put 12 in that. So 12 in equation number 11, that gives me the S of f. This implies the S of f is equal to, I can see that there is a g delta of f uh, into this function, that is t times sinc of the f into capital T into e to the power minus j pi ft. Right? Okay, so I'll put this back. I think we have another function over there. Yes. So that means that's equal to substituting the g delta of f in the format. There is a fs already present. Into this t comes into picture, right? fst. I'll bring the sinc function outside because it has nothing to do with the summation. All right. So this is the sinc of ft into e to the power minus j pi ft, and then you write the summation, because summation is applicable only for the term containing n, that is minus infinity to plus infinity, the g of f minus n fs. So call this as equation number 30. Now again we'll do the same thing which we did in the previous sessions, wherein you can see that put n equal to 0, right? When I put n equal to 0, so right, I can see that at the center, right, it is g of f. I still have the g of f. All right, I have the g of f present, and I can also see that, right, the various frequency components that are present at n equal to different, when I put n equal to different value, they get truncated by sinc function as well as the e to the power function. There are right. So e to the power minus j pi ft is the one which is used to which is a decaying function. I can see that at 0 it has a maximum value, and as I progress towards the plus or minus infinity, right, of f, it decreases. So you see that its amplitude is going to be decreasing, right, at f equal to plus or minus fs, plus or minus 2fs, 3fs, and so on. As you increase the n value, right, the spectral replicates are going to be uh, I can say attenuated. They get attenuated. So there is a sinc function in this particular expression. The sinc function is actually a low pass filter, correct? So if you remember, on the frequency domain, the sinc function, right? I think I can draw that here. So let's look at the before discussing about this equation 13. Let's look at this the magnitude the spectrum of h of f once, because this is the equation we got, equation number 12, right? The magnitude and the phase spectrum, let me try to write. Okay, so from 12, the magnitude and the phase spectra can be plotted. So that's what we are trying to do now. So This is the frequency. First, we'll plot the magnitude. Sorry. Okay, this is magnitude of h of f. So we know this. This actually begins with the highest value and it comes down to a lower value. Again, it goes up, comes down, goes up, down, and so on. Same thing will be repeated on the other side. So it comes down to zero like this and this and so on. You can see that this is what is happening. So at this is 0, you have a magnitude amplitude of capital T at the top. This is 1 by capital T, this is 2 by capital T, and so on. This is 3 by capital T, this is minus 1 by T, minus 2 by T, minus 3 by T, and so on. So this is the magnitudes plot, and the phase. For plotting the phase, I need only, see, this is my magnitude. T sync function I plotted. Okay. But magnitude is over. This is the magnitude. This is the theta, e to the j theta for me. So j theta is pi ft. So that's the minus, sorry, it's actually minus pi ft. Theta can be identified as minus pi ft. Minus indicates that it's a straight line, y equal to mx, right? But it is a decaying function. It's decreasing. All right. So these are the points I have. I still retain 1 by t, 2 by t, 3 by t, minus 1 by t, minus 2 by t, minus 3 by t, and so on. This is still the frequency axis. Now I'm plotting the theta of f. Okay. So that will be a decaying function, right? Let me just plot a decaying function like this. It passes through origin and it will pass through this. Okay, so it will be varying from between plus pi and minus pi. Okay, so 1 by t, 2 by t, 3 by t, minus 1 by t, minus 2 by t, minus 3 by t, and so on. All right, so this is how it's going to vary. Right, now it's very clear that we are in the frequency domain, and this function, the h of f, whatever I have, is actually a low pass filter. It's in the frequency domain, right? In the frequency domain, it actually passes the values up to 1 by t, right? And it tries to attenuate after this region. So you can see that this and this, it's an attenuation, right? So I'll go back to the equation 13 and I'll see that there is a sinc function still existing, right? You see in my final answer, that is S of f, that is equation number 13, I still have this T sync into e to the power is still there. So T sync is my magnitude, e to the power is a decay, right? It's a phase, right? Phase component. So my g of f minus nfs, right, located at different positions, get multiplied by this, right? Which means it's there is a low pass filtering action that is being taken place automatically by this, right? So that's my point, right? So okay, let's try to write whatever we can conclude from equation 30. From 13, our conclusion is this. Okay, from 13, uh, there are spectral replicates of the G, I can write, yeah, it's G delta of F itself. Okay, G delta of F located at F equal to plus or minus fs plus or minus 2fs and so on. Okay, so these are the positions where we find the spectral replicates of the given function, right? And now I understand that they are going to be multiplied by sinc of ft. So that's the first point. They are present at these locations. The spectral replicas get multiplied, or I can write R multiplied by the sinc function, sinc of ft. Okay, spectral replicas are multiplied by the sinc ft function. Means what? They are attenuated. Okay, means they get attenuated. First thing, right? So whenever it attenuates, right? So I try to draw something. It may not be accurate, but still. So you see, any again this diagram you don't have to write whenever any question comes. Normally, I see I have a central g of f, and the next ones will be attenuated according to like this. Okay, it's actually getting multiplied by some functions, maybe so that means if you have a triangle here and a triangle here, you see that it's always right lesser in magnitude as that as you move away from your central position. Say this is f equal to 0 and I'm actually in the frequency axis, let's assume. So this is my f axis. I'm present on the frequency axis, and it's very clear that as I move, the magnitude of the triangles, whatever we are writing, it keeps on reducing, right? So because of which this is going to help you the in the reconstruction, because reconstruction is going to happen only at this, right? Even if this gets extended something like this, no problem, right? So that's what is my next statement, right? They get attenuated. So I already wrote earlier, I'll continue there. So the spectral replicates are multiplied by the sinc ft, which means they get attenuated. And so because of this attenuation, right, they are actually attenuated, they are getting attenuated, and it itself help in the reconstruction filter, in the recovery of the g of t from g delta of t, right? And okay, they get attenuated and it helps, or I can write help, and they help in the reconstruction, help in the reconstruction of g of t from the g delta of t. Okay, now we need to talk about the sinc function again. So the sinc function in this expression of h of f means it is a low pass filter, and it attenuates the upper portion of the spectrum that is centered at f equal to 0. Okay, now you see, this is going to happen if your message spectrum is in the same thing. I'll try to draw. Let me assume that my message spectrum is something like this. Okay, if at all it is like this, you see that you lose some portion of your higher message frequencies, correct? So there is a name for this particular, again this is evident in the flat top sampling. Whatever you lose here, right, there is a name for that. you lose your higher frequency component of the message spectrum located at f equal to 0. We are not bothered about what's going to happen outside this. We are not worried. Okay, only in the only the that particular spectrum which is centered at f equal to 0, it might lose something, right? If at all the sync function, right, is the first lobe of your sync function falls well inside your the first spectrum that is located at f equal to 0. If that is the case, we lose the high frequency content. It is called as an aperture effect. This is important. You need to mention this. Okay, aperture effect, right? Let me write that point here. Okay, so the sync function in the expression of h of f. I'll give an equation for reference as well. That is in 12. Okay, the expression of h of f in equation number 12. Okay, it actually suggests you something. That is suggests that it acts like a LPF. Okay, now if it's a normal LPF and right, like our first case, no problem, right? But sometimes it may attenuate the upper portion of the message spectrum, right? So sometimes this may attenuate the upper portion of message spectrum at f equal to 0, right? I am talking about the triangle, right, which is at the center, only this triangle, right? If at all the triangle is like the red colored one, then only we have a problem. If you have a black colored one, no issues. Okay, that's why we wrote sometimes. Okay, right. Attenuates the what I wrote, upper portion of the spectrum at f equal to 0, right? Okay, what happens when this happens at f equal to 0, comma, causing the loss of the high frequency contents by a process that is called as the aperture effect. So how do you control this? Again, I'll check out what is this. In this, okay, by a name, this is called as aperture effect. So this means if you have a larger pulse duration t, there will be larger effect of the aperture effect. So that's how you need to keep the pulse duration as shorter as possible. That's the whole idea here. Okay, so larger the t implies larger aperture effect. So the whole aperture effect can be compensated by using an equalizers, right, of certain magnitude response in cascaded with the reconstruction filter, right? That's the whole idea we have to follow in order to compensate this. So there are some devices used. They are called as equalizers. Using the equalizers, you can actually compensate the uh, effect of aperture. Okay, so this will be the last sentence. Equalizers can be used in cascade with the reconstruction filter to compensate the aperture effect.